Okay, today I'll be talking about linear and angular terms and how to convert between the two. For example, let's look at a group of skaters, 5 skaters with the same angular velocity. That means they go through the same amount of radians per second, but they have very different linear speeds because if you look at it, the person on the outside would have to cover a lot more arc length per unit time than the person on the inside. Now there's also a difference between tangential velocity and tangential speed. Tangential speed really only gives you the magnitude of that vector quantity of tangential velocity. So let's see if we can come up with some type of conversion between radians per second and meters per second. Now obviously, as we just talked about in the slide before, the further out you are, you're going to have a greater tangential speed because you're going to have to cover more arc length. So we know that the tangential speed is going to be dependent on the radius. So let's see how this comes out. Now we know that velocity tangential, or regular velocity, is equal to distance over time. But we also know that this distance, the arc length, is equal to theta times r. So then we can actually isolate theta over t, and we know that that is angular speed. So now we can actually have an expression for velocity tangential. Velocity tangential would equal to r times omega. Now the omega has to be in radians per second, and just as we noted before, it does vary directly with how far out you are. So the further out you are, the greater the tangential speed. Okay? Alright, let's see if we can do the same thing now for acceleration. Can we relate angular acceleration to linear acceleration? Well, we know that linear acceleration is this equal to change in velocity over change in time. And we know that velocity tangential is equal to r omega from the prior slide. So we can replace all the velocity tangentials with r omegas. Then we could factor out the r's. And we know omega final minus omega initial over t is acceleration. So therefore, we have an expression for acceleration tangential is equal to r times alpha. And once again, alpha has to be in radians per second squared. Okay. Let's try an example of this. A helicopter blade has an angular speed of 6.5 revolutions per second and an angular acceleration of 1.3 revolutions per second. For point 1 on the blade, okay, this point here, which is 3 meters out, we would like to find the magnitude of the tangential speed, like how fast it would go off on a tangent, and the tangential acceleration, how fast that linear speed is increasing or decreasing. All right. So the first thing we have to actually do is we have to remember that we have to convert everything into radians. So we have a speed that's 6.5 revolutions per second. We have to convert that into radians. And once again, remember that 1 revolution is the same thing as 2 pi radians, and that comes out to be 40.8 radians per second. And the same thing is true with alpha. We have to convert that from revolutions per second squared into radians per second squared, and using the same conversion. Okay, now we have things in radians, and we can go ahead and find out our linear equivalence, or our speed tangential out at that radius, and our acceleration tangential out at that radius. So it's pretty straightforward. So you can actually go from angular terms to tangential terms, and from tangential terms back into angular terms if you wish. Just do the opposite way. All right. This is kind of common sense, but it's worth noting. The tangential speed of a point of an outer edge of a tire is equal to the speed of the car over the ground. And this assumes there's no slipping, right? So we know that velocity is equal to r omega. Okay? And that's velocity tangential. The tangential acceleration on the outer edge of the tire is equal to the acceleration of the car over the ground as well. and that would be equal to r times alpha. Let's give an example of this. Starting from rest, a car accelerates for 20 seconds with a constant linear acceleration of 0.800 meters per second squared. The radius of the tire is 0.330 meters. What is the angle through which each wheel has to rotate? Okay, so now we're starting with linear terms and we're trying to get angular terms. So it's the exact opposite of what we did before. Okay. First, you need to calculate the angular acceleration from the linear acceleration. So we know that the angular acceleration would be the tangential acceleration divided by r. So that comes out to be 2.42 radians per second. Now, let's summarize the terms that were given to us. We are looking for how much radiance it goes through. What's the angular displacement? We know the angular acceleration. We don't know the final velocity. We know the initial angular speed was 0, and we knew it took 20 seconds. So we need to solve for the unknown angular displacement. And we'll just use simply this equation. And we know each of the terms. So we could just plug in numbers and get how many radians it went through. The initial speed was 0, so that term drops out, and you're just left with 1/2 the angular acceleration times time squared. So it comes out to be negative 484 radians.